Data Engineering: Analyzing Big Data and Modern Data. Written by Phil Gilbert. Narrated by Kevin Brooker. Preface: Welcome to the world of data engineering, where the raw material of the digital age, data, is transformed into actionable insights that drive decisions, innovations, and advancements across industries. This book is your gateway into understanding and mastering the essential principles, practices, and technologies that underpin the field of data engineering. In today's data-driven economy, organizations increasingly rely on robust data infrastructures and efficient data pipelines to harness the power of information. Data engineering is the backbone of this infrastructure, encompassing the design, implementation, and maintenance of systems that enable the collection, storage, and processing of vast amounts of data. This book is designed as a comprehensive guide for anyone seeking to embark on a journey into data engineering or looking to deepen their understanding of its intricacies. Whether you are a seasoned data professional, a software engineer transitioning into data roles, or a student eager to explore the forefront of technological innovation, this book will equip you with the knowledge and skills necessary to navigate the complexities of modern data ecosystems. Each chapter is crafted to provide a blend of theoretical foundations, practical insights, and hands-on examples to help you on your way. So, let's get started. Chapter 1: Introduction to Data Engineering. Data engineering involves designing architectures that allow data to be processed efficiently and transformed into formats that can be readily used for analysis, machine learning, and decision-making. 1.1. What is data engineering? Data engineering is a field within data science that focuses on practical applications of data collection and analysis. It involves designing, constructing, installing, and maintaining the systems and architecture necessary to collect, store, and analyze data. 1.2. Importance in the modern data landscape. Data engineering is the discipline focused on the practical application of data collection, transformation, and storage to support data analysis and business decision-making. It involves the creation and maintenance of data pipelines that enable the efficient processing and management of data across various systems. 1.3. Key concepts and terminologies. In data engineering, several key concepts and terminologies are fundamental to understanding and working effectively in the field. Here are some of the most important ones. 1. Data pipeline. A data pipeline refers to the series of processes and tools used to automate the movement and transformation of data from source systems to destinations like data warehouses or data lakes. 2. ETL. Extract, transform, load. Extract. The process of retrieving raw data from various data sources. Transform. The process of cleaning, normalizing, and structuring data to meet the requirements of the destination system. Load. The process of importing the transformed data into the final storage system. 3. Data warehouse. A centralized repository for storing structured data from multiple sources, optimized for querying and analysis. 4. Data lake. A storage repository that holds vast amounts of raw data in its native format until it is needed. Unlike data warehouses, data lakes can store structured, semi-structured, and unstructured data. 5. Data mart. A subset of data warehouse focused on a specific business area or team, providing targeted data access and analysis capabilities. 6. Big data. Refers to extremely large data sets that cannot be handled using traditional data processing tools. Big data often requires specialized technologies such as Hadoop, Spark, and distributed databases. 7. Batch processing. A method of processing large volumes of data at once, typically on a scheduled basis. Batch processing is suitable for tasks that do not require real-time data updates. 8. Stream processing. A method of processing data in real time as it is generated. Stream processing is essential for applications that require immediate data insights and actions. 9. Data integration. The process of combining data from different sources to provide a unified view. Data integration ensures consistency and accuracy across merged datasets. 10. Data governance. A framework for managing the availability, usability, integrity, and security of data. Data governance involves policies, procedures, and standards to ensure data quality and compliance. 11. Data cleaning or data cleansing. The process of detecting and correcting errors or inconsistencies in data to improve data quality. This includes removing duplicates, filling in missing values, and correcting inaccuracies. 12. Schema. The structure that defines the organization of data within a database, including tables, fields, and relationships between them. 13. Indexing. A database optimization technique that improves the speed of data retrieval operations. Indexes are created on database columns to enable faster query performance. 14. Data modeling. The process of creating a data model that defines how data is structured and related within a database or data warehouse. Data modeling includes conceptual, logical, and physical models. 15. Scalability. The ability of a system to handle increasing volumes of data and workload without compromising performance. Scalability can be achieved through vertical scaling, or adding more resources to a single node, or horizontal scaling, adding more nodes to a system. 16. APIs, or Application Programming Interfaces. Interfaces that allow different software systems to communicate and exchange data. APIs are crucial for integrating various data sources and applications. 17. OLAP, or OLAP, Online Analytical Processing. A category of data processing that enables complex queries and analysis, often used in data warehousing and business intelligence. OLAP systems are designed for quick response times to multi-dimensional analytical queries. 18. OLTP, Online Transaction Processing. A category of data processing focused on managing transaction-oriented applications. OLTP systems are optimized for fast query processing and maintaining data integrity in multi-access environments. 19. Metadata. Data that describes other data, providing information about the data's source, structure, transformations, and usage. Metadata is essential for data management and governance. 20. Data orchestration. The coordination and management of data workflows and processes to ensure data moves smoothly and efficiently through the pipeline. Data orchestration tools help automate and monitor complex data workflows. Understanding these key concepts and terminologies is essential for anyone working in or aspiring to work in the field of data engineering. 1.4. Historical evolution of data engineering. The field of data engineering has evolved significantly over the past several decades, driven by advancements in technology, the increasing volume of data, and the growing demand for data-driven insights. Here is an overview of its historical evolution. Early data processing, 1950s to 1970s. Mainframe computers. In the 1950s and 1960s, data processing was conducted on mainframe computers. These early systems handled batch processing tasks such as payroll and inventory management. File systems. Data was stored in flat file systems, and data management was rudimentary. Manual intervention was often required for data integration and processing tasks. Relational databases, 1970s to 1980s. Introduction of RDBMS. The development of relational database management systems, or RDBMS, in the 1970s, such as IBM's System R and Oracle, revolutionized data storage and retrieval. The relational model proposed by E.F. Codd allowed for more efficient and flexible data management. SQL, Structured Query Language. SQL became the standard for querying and managing data in relational databases, making data manipulation more accessible. Data warehousing, 1980s to 1990s. Data warehouses. In the late 1980s and 1990s, the concept of data warehousing emerged. Data warehouses centralized data from various sources, optimized for analytical queries rather than transactional processing. ETL processes. Extract, transform, load. ETL processes became essential for moving and transforming data into warehouses. ETL tools like Informatica and DataStage gained prominence. Big data and distributed systems, 2000s. Big data. The 2000s saw an explosion in the volume, variety, and velocity of data, often referred to as big data. Traditional databases struggled to handle such large-scale data. Hadoop. The introduction of Hadoop, an open source framework for distributed storage and processing of large data sets, marked a significant milestone. Hadoop's HDFS, or Hadoop Distributed File System, and MapReduce programming model enabled efficient big data processing. NoSQL databases. NoSQL databases like MongoDB, Cassandra, and HBase emerged to handle unstructured and semi-structured data, providing scalable and flexible alternatives to traditional RDBMS. Real-time data processing, 2010s. Stream processing. Technologies like Apache Kafka, Apache Storm, and Apache Flink enabled real-time data processing, allowing for immediate insights and actions based on live data streams. Cloud computing. The rise of cloud platforms, e.g., AWS, Google Cloud, Microsoft Azure, provided scalable and cost-effective infrastructure for data storage and processing. Services like Amazon Redshift, Google BigQuery, and Azure Synapse Analytics simplified data warehousing and analytics in the cloud. Modern data engineering, 2020s. Data lakes. Data lakes, which store raw data in its native format, became popular for handling diverse and large datasets. Tools like Apache Hadoop and AWS S3 are commonly used for building data lakes. Data lakehouses. Combining the best features of data warehouses and data lakes, data lakehouses, e.g., Databricks, provide structured storage with the flexibility of a data lake. ETL to ELT. The paradigm shifted from ETL to ELT, extract, load, transform, where raw data is first loaded into the data storage system and transformation occurs later. This shift is facilitated by the increasing processing power of modern data warehouses and data lakes. Automation and orchestration. Tools like Apache Airflow, Prefect, and DeepBT, or Data Build Tool, automate and orchestrate complex data workflows, ensuring data pipelines are efficient and reliable. Data Ops and DevOps integration. Data engineering practices increasingly integrate with DevOps methodologies, emphasizing automation, continuous integration, and continuous delivery in data pipelines. Future trends. AI and machine learning. Integration of AI and machine learning in data engineering for intelligent data processing and predictive analytics. Serverless architectures. Adoption of serverless computing for scalable and cost-effective data processing. Privacy and security. Enhanced focus on data privacy and security, driven by regulations like GDPR and CCPA. The evolution of data engineering reflects the broader technological advancements and the growing importance of data in driving business insights and decisions. Chapter 2. Data collection and ingestion. Data collection and ingestion are critical stages in the data engineering lifecycle. They involve gathering data from various sources and bringing it into a system where it can be processed and analyzed. This chapter covers the fundamental concepts, methods, and tools associated with data collection and ingestion. 2.1. Data sources: structured, semi-structured, and unstructured. Understanding the different types of data is essential for effective data management and utilization. Data is generally categorized into 3 types based on its structure: structured, semi-structured, and unstructured. Each type has unique characteristics and use cases. Structured data is highly organized and stored in a predefined format, usually in rows and columns. It is easily searchable due to its organization and can be queried and analyzed using standard tools like SQL. The structure or schema of structured data is predefined and doesn't change frequently. Examples of structured data include relational databases such as MySQL, Oracle, and SQL Server, spreadsheets like Excel files, and transactional data such as financial transactions and inventory records. This type of data is commonly used for business reporting, data warehousing, and operational systems to manage day-to-day business operations. Semi-structured data, on the other hand, has a flexible structure. It does not follow a fixed schema, but includes some organizational properties through tags or markers, making it self-describing. This type of data can handle diverse formats. Examples of semi-structured data include XML files, JSON files, and NoSQL databases like MongoDB and Cassandra. It is often used for web data exchange, such as API responses and requests, configuration files, and document stores where documents with varying structures are stored. Unstructured data lacks any predefined structure or schema and can encompass large and complex data sets. It includes diverse types such as text, multimedia, and binary data. Examples of unstructured data are text files like emails, word processing documents, and PDFs, multimedia files such as images, audio, and video, and social media content like tweets, posts, and comments. This type of data is used in content management to handle large volumes of documents, images, and videos, text mining to extract information from text data, and big data analytics to analyze large, diverse data sets for patterns and insights. In comparing these types, structured data is easier to manage and analyze due to its organized format, whereas unstructured data is more flexible but requires advanced tools for processing and analysis. Semi-structured data provides a balance, offering some level of organization while accommodating a flexible schema, making it useful for applications that require both structure and flexibility. Understanding the characteristics and use cases of structured, semi-structured, and unstructured data is crucial for choosing the right tools and techniques for effective data utilization. Each type requires different approaches for storage, management, and analysis, underscoring the importance of selecting the appropriate method for the specific data type. 2.2 Data ingestion techniques and tools. Data ingestion refers to the process of collecting, importing, and processing data from various sources into a storage or processing system for further use. Effective data ingestion is crucial for maintaining data integrity, ensuring timely access to data, and enabling comprehensive data analysis. There are several techniques and tools available for data ingestion, each suitable for different types of data and use cases. Data ingestion techniques. Batch ingestion. Batch ingestion involves collecting and processing data in large chunks or batches at scheduled intervals. This method is suitable for scenarios where real-time data processing is not critical. Batch ingestion is often used for processing log files, aggregating data from different sources, and performing ETL, or extract, transform, load operations. Real-time streaming ingestion. Real-time ingestion processes data as it is generated or received, allowing for immediate analysis and action. This technique is essential for applications requiring up-to-the-minute data, such as monitoring systems, fraud detection, and online recommendation engines. Real-time ingestion handles continuous data streams and ensures low latency. Microbatch ingestion. Microbatch ingestion is a hybrid approach that combines elements of batch and real-time ingestion. Data is collected and processed in small, frequent batches, providing a balance between timely data processing and resource efficiency. This technique is suitable for applications that need near real-time data updates but can tolerate slight delays. File-based ingestion. File-based ingestion involves importing data from various file formats, such as CSV, JSON, XML, and others. This method is often used when dealing with semi-structured or unstructured data. It is suitable for scenarios where data is stored in files and needs to be ingested periodically or on demand. Database ingestion. Database ingestion involves extracting data from traditional relational databases or NoSQL databases. This technique can use methods like change data capture, or CDC, to track and ingest changes from source databases in near real time. It is useful for maintaining up-to-date data in data warehouses or analytical systems. Data ingestion tools. Apache Kafka. Apache Kafka is a distributed streaming platform that can handle real-time data ingestion and processing. It is designed for high throughput and fault-tolerant data streams, making it suitable for real-time analytics, monitoring systems, and data integration. Apache NiFi. Apache NiFi is a data integration tool that provides a web-based interface for designing data flows. It supports real-time and batch ingestion and can handle data from various sources, including databases, files, and message queues. NiFi's ease of use and flexibility make it ideal for building complex data workflows. Apache Flume. Apache Flume is a distributed, reliable, and available service for efficiently collecting, aggregating, and moving large amounts of log data. It is particularly useful for ingesting log data into centralized storage systems like Hadoop HDFS or cloud storage. Logstash. Logstash, part of the Elastic Stack, is an open source tool for collecting, parsing, and storing logs for future use. It supports a wide variety of input sources and can transform data before sending it to a storage system like Elasticsearch. Talend. Talend is an open source data integration tool that provides a comprehensive suite of tools for ETL, data quality, and data management. It supports both batch and real-time data ingestion and can integrate with various data sources, making it suitable for complex data integration scenarios. AWS Glue. AWS Glue is a fully managed ETL service provided by Amazon Web Services. It can automatically discover and categorize data from various sources, generate ETL scripts, and manage the execution of these scripts. Glue is well suited for integrating data in the AWS ecosystem. Google Cloud Data Flow. Google Cloud Data Flow is a fully managed stream and batch processing service provided by Google Cloud Platform. It supports real-time data ingestion and processing using Apache Beam, allowing for scalable and efficient data pipelines. Choosing the right data ingestion technique and tool depends on the specific requirements of the data environment, such as the volume, velocity, and variety of data, as well as the need for real-time processing. Understanding the strengths and use cases of each technique and tool helps in designing efficient and effective data ingestion pipelines, ensuring that data is readily available for analysis and decision-making. 2.3. Real-time versus batch data processing. Real-time and batch data processing are two fundamental approaches for handling data, each offering unique benefits and applications. Real-time data processing involves analyzing data as it is generated or received, providing immediate insights, low latency, continuous monitoring, streamlined operations, and dynamic adaptation. This approach is essential for applications such as fraud detection, sensor data analysis, monitoring systems, recommendation engines, and real-time bidding in advertising. On the other hand, batch data processing involves processing data in large chunks or batches at scheduled intervals. It offers scalability, resource efficiency, robustness, the ability to perform complex analysis, and cost effectiveness. Batch processing is commonly used in data warehousing, ETL operations, reporting and analytics, and historical trend analysis. The choice between real-time and batch processing depends on factors such as data freshness requirements, processing time constraints, resource availability, and use case complexity. Organizations often use a combination of both approaches to optimize performance, efficiency, and cost effectiveness, leveraging the strengths of each method for different data processing needs. 2.4. Handling data quality and integrity. Handling data quality and integrity is crucial for ensuring the reliability, accuracy, and usefulness of data for decision-making and analysis. Several steps and practices are essential for maintaining data quality and integrity throughout its lifecycle. Data profiling and assessment. Begin by understanding the characteristics and quality of the data. Data profiling involves analyzing the content, structure, and relationships within the data to identify inconsistencies, anomalies, and errors. Data cleaning and standardization. Cleanse the data by correcting errors, removing duplicates, filling missing values, and standardizing formats. This process involves data consistency and accuracy, ensuring that it adheres to defined standards and conventions. Data validation and verification. Validate data against predefined rules, constraints, and reference data to ensure its correctness and completeness. Verification involves cross-checking data with external sources or validating it through independent means to confirm its accuracy. Implementing data governance. Establish data governance policies, processes, and controls to ensure accountability, transparency, and compliance with regulatory requirements. Data governance frameworks define roles and responsibilities, data ownership, and procedures for managing data quality and integrity. Metadata management. Maintain metadata which provides context and information about the data, including its source, lineage, quality, and usage. Metadata management facilitates data discovery, understanding, and traceability, enabling better decision-making and data governance. Data quality monitoring. Continuously monitor data quality metrics such as completeness, accuracy, consistency, and timeliness to identify issues and trends proactively. Automated monitoring tools can help detect anomalies and trigger alerts for further investigation and remediation. Data security and privacy. Protect data from unauthorized access, manipulation, or disclosure by implementing robust security measures and access controls. Ensure compliance with data privacy regulations such as GDPR and CCPA by anonymizing sensitive data and obtaining consent for data processing. User training and awareness. Educate users about the importance of data quality and integrity, and train them on best practices for data entry, manipulation, and usage. Foster a culture of data stewardship and responsibility throughout the organization to promote data quality as a shared responsibility. Data quality improvement initiatives. Establish continuous improvement initiatives to address root causes of data quality issues and enhance data management processes. Conduct regular reviews, audits, and feedback loops to identify areas for improvement and implement corrective actions. By implementing these practices and adopting a proactive approach to data quality and integrity management, organizations can ensure that their data assets are reliable, accurate, and trustworthy, enabling informed decision-making and driving business success. Chapter 3: Data Storage Solutions. Data storage solutions are essential components of any organization's data infrastructure, providing reliable, scalable, and efficient storage for managing and accessing data. 3.1: Relational databases and data warehouses. Relational databases and data warehouses are both data storage solutions commonly used in organizations, but they serve different purposes and have distinct characteristics. Relational databases. Relational databases are designed to store structured data in tables with rows and columns, following a predefined schema. They use SQL or structured query language for querying and managing data. Here are some key features. Structured data storage. Relational databases organize data into tables with well-defined schemas, enforcing data integrity and consistency. ACID transactions. They support ACID, atomicity, consistency, isolation, durability transactions, ensuring data reliability and consistency. Optimized for OLTP. Relational databases are optimized for online transaction processing, or OLTP, workloads, such as handling transactions, managing customer data, and supporting real-time operations. Normalized data model. They typically use a normalized data model to minimize redundancy and improve data consistency. Data warehouses. Data warehouses are specialized databases optimized for storing and analyzing large volumes of data from multiple sources. They facilitate complex queries and data analysis for decision-making. Here are some key features. Aggregated data storage. Data warehouses store aggregated and historical data from various sources, providing a unified view for analysis and reporting. Optimized for OLAP. They are optimized for online analytical processing, or OLAP workloads, such as data mining, trend analysis, and business intelligence. Denormalized data model. Data warehouses often used a denormalized or star schema model to optimize query performance and facilitate analytical operations. Data transformation. They include features for data cleansing, transformation, and integration to prepare data for analysis. Scalable and performance-tuned. Data warehouses are designed to handle large data sets and complex queries efficiently, often utilizing parallel processing and optimized storage mechanisms. Relationship and integration. While relational databases and data warehouses serve different purposes, they are often complementary and integrated within an organization's data architecture. Data extraction and loading. Data warehouses often source data from operational systems stored in relational databases through ETL, extract, transform, load processes. Data marts. Data warehouses may include data marts, which are subsets of data tailored for specific departments or business units, often derived from relational databases. Reporting and analysis. Relational databases may serve as transactional systems, while data warehouses provide a centralized repository for analytical processing, reporting, and decision support. In summary, relational databases are optimized for transactional processing and structured data storage, while data warehouses are specialized for analytical processing and handling large volumes of data for decision-making. Integrating these solutions allows organizations to manage both transactional and analytical data effectively, supporting diverse business needs. 3.2. NoSQL databases. Key value, document, column family, graph. NoSQL databases offer alternative approaches to data storage and retrieval compared to traditional relational databases. Here's an overview of 4 common types of NoSQL databases: key value, document, column family, and graph. Key value stores. Key value stores are the simplest form of NoSQL databases, where each data item is stored as a key value pair. Here are some key features. Simple data model. Data is stored as key value pairs, where each key is unique and associated with a value. Fast and scalable. Key value stores are highly scalable and optimized for high throughput and low latency operations. Flexible schema. They offer a flexible schema, allowing different keys to have values of different types. Examples: Redis, Amazon DynamoDB, RAYAC. Document databases. Document databases store semi-structured data as documents, typically in JSON or BSON format. Here are some key features. Document-oriented. Data is stored as documents, which can contain nested structures and arrays. Schema flexibility. Document databases offer schema flexibility, allowing each document to have its own structure. Query flexibility. They support rich query capabilities, including querying by field, range queries, and aggregation. Examples: MongoDB, Couchbase, Elasticsearch. Column family stores. Column family stores organize data in columns rather than rows, making them suitable for wide column stores. Here are some key features. Column-oriented storage. Data is stored in columns, grouped together into column families, allowing efficient retrieval of specific columns. Schema flexibility. Column family stores offer schema flexibility within each column family. Scalability. They are designed for high scalability and can handle large volumes of data. Examples: Apache Cassandra, HBase, ScyllaDB. Graph databases. Graph databases are designed for storing and querying graph-like data structures consisting of nodes, edges, and properties. Here are some key features. Graph data model. Data is represented as nodes or entities and edges or relationships between nodes, allowing for complex graph traversals. Relationship-centric queries. Graph databases excel at relationship-centric queries, such as finding shortest paths, recommendations, and network analysis. Schema flexibility. They offer schema flexibility, allowing nodes and edges to have properties dynamically. Examples: Neo4j, Amazon Neptune, Janus Graph. Use cases: key value stores, caching, session management, real-time analytics. Documents databases, content management, user profiles, product catalogs. Column family stores, time series data, sensor data, recommendation engines. Graph databases, social networks, fraud detection, recommendation systems. NoSQL databases offer a variety of options for storing and querying data, allowing organizations to choose the best fit for their specific use cases and requirements. 3.3. Data lakes and lakehouses. Data lakes and lakehouses are both modern approaches to storing and analyzing large volumes of diverse data. While they share similarities, they have distinct characteristics and use cases. Data lakes. Data lakes are centralized repositories that store raw, unstructured, semi-structured, and structured data at scale. Here are some key features. Storage for raw data. Data lakes store data in its raw format, without the need for predefined schemas or transformations, enabling flexibility and agility. Scalability. They are designed to scale horizontally and accommodate massive volumes of data from various sources, including structured databases, log files, sensor data, social media feeds, and more. Schema on read. Data is stored first and structured later, allowing users to apply different schemas and interpretations when querying or analyzing the data. Hadoop ecosystem integration. Data lakes often leverage Hadoop-based technologies like HDFS, Hadoop Distributed File System, Spark, and Hive for storage and processing. Data exploration and discovery. Data lakes enable data scientists, analysts, and other users to explore and discover insights from diverse datasets, fostering innovation and discovery. Data lakehouses. Data lakehouses combine the flexibility of data lakes with the reliability and performance of data warehouses, bridging the gap between raw data storage and structured analytics. Here are some key features. Unified storage and processing. Data lakehouses provide a unified platform for storing and processing both raw and structured data, offering the best of both worlds. Schema enforcement and evolution. They support schema enforcement and evolution, allowing users to define and enforce schemas for structured data while maintaining flexibility for unstructured data. ACID transactions. Data lakehouses ensure transactional consistency and reliability for analytical workloads, supporting ACID, atomicity, consistency, isolation, durability properties. Optimized query performance. They leverage optimized storage formats and indexing techniques to improve query performance for analytical workloads, enabling faster data retrieval and analysis. SQL compatibility. Data lakehouses support SQL-based querying and analytics, making it easier for users to interact with and analyze data using familiar tools and languages. Use cases. Data lakes. Data lakes are suitable for storing diverse raw data types, supporting data exploration, machine learning, and advanced analytics use cases. Data lakehouses. Data lakehouses are ideal for organizations that need both flexibility and reliability in their data storage and analytics platform, supporting a wide range of analytical workloads, including reporting, dashboarding, ad hoc querying, and data science. In summary, data lakes and lakehouses offer flexible and scalable solutions for storing and analyzing large volumes of data. Data lakes provide a centralized repository for raw data storage and exploration, while lakehouses extend this concept by adding schema enforcement, query optimization, and transactional capabilities, making them suitable for a broader range of analytical use cases. 3.4. Choosing the right storage solution. Choosing the right storage solution depends on various factors, including the type of data, scalability requirements, performance needs, budget constraints, and specific use cases. Here's a step-by-step guide to help you choose the right storage solution for your needs. 1. Assess data characteristics. Data type. Determine whether your data is structured, semi-structured, or unstructured. This will influence the choice of storage solution. Volume. Consider the amount of data you need to store and its growth rate over time. Velocity. Evaluate the speed at which data is generated, ingested, and processed. Variety. Determine the diversity of data types and formats, such as text, images, videos, or sensor data. 2. Define use cases. Transactional processing. If you need to support transactional workloads with ACID properties, consider relational databases or new SQL databases. Analytical processing. For analytics, reporting, and data warehousing use cases, consider data warehouses or data lakehouses. Real-time processing. If you require low-latency access to data for real-time analytics or operational insights, consider streaming platforms or in-memory databases. Mixed workloads. If you need to support both transactional and analytical workloads, consider hybrid solutions or data lakehouses. 3. Consider scalability and performance. Scalability. Assess whether the storage solution can scale horizontally to handle increasing data volumes and concurrent users. Performance. Evaluate the solution's performance characteristics, including throughput, latency, and response times to ensure it meets your performance requirements. 4. Evaluate cost. Upfront cost. Consider the initial investment required for hardware, software licenses, and infrastructure setup. Operating costs. Assess ongoing costs, including maintenance, support, cloud storage fees, and operational expenses. Total cost of ownership, or TCO. Compare the TCO of different storage solutions over their life cycle to make an informed decision. 5. Ensure data security and compliance. Data security. Evaluate the security features offered by the storage solution, including encryption, access controls, authentication mechanisms, and compliance certifications. Regulatory compliance. Ensure that the storage solution complies with relevant data protection regulations, industry standards, and compliance requirements such as GDPR, HIPAA, or PCI DSS. 6. Consider integration and ecosystem. Ecosystem compatibility. Assess whether the storage solution integrates seamlessly with your existing data infrastructure, tools, and applications. Vendor lock-in. Consider the risk of vendor lock-in and evaluate whether the storage solution offers interoperability and portability options. 7. Future-proofing. Flexibility. Choose a storage solution that can adapt to evolving business needs, technological advancements, and changing data requirements. Vendor roadmap. Assess the vendor's commitment to innovation, product development, and long-term support to ensure continued relevance and support. By considering these factors and conducting a thorough evaluation, you can choose the right storage solution that aligns with your organization's goals, requirements, and budget constraints, enabling you to effectively store, manage, and leverage your data assets. Chapter 4. Data Transformation and Processing. Data transformation and processing are essential steps in the data lifecycle, involving the conversion, manipulation, and analysis of data to derive insights and support decision-making. 4.1. ETL. Extract, transform, load processes. ETL, extract, transform, load processes, are fundamental to data integration and warehousing, facilitating the extraction of data from various sources, its transformation into a suitable format, and loading it into a target data repository. Here's an overview of each stage. Extract. Extract involves retrieving data from multiple sources, which can include databases, files, APIs, logs, or streaming data sources. Key considerations during the extraction phase include identifying the source systems and data to be extracted, selecting appropriate extraction methods, such as full or incremental extraction, ensuring data integrity and consistency during extraction. Transform. Transform involves cleaning, filtering, and structuring the extracted data to make it suitable for analysis and storage. This phase includes cleaning and validating data to remove duplicates, errors, and inconsistencies. Performing data transformations such as normalization, aggregation, or joining multiple datasets. Enriching data by adding derived fields, calculations, or business logic. Conforming data to a standardized format or schema. Load. Load involves loading the transformed data into a target data repository, such as a data warehouse, data lake, or operational database. Key considerations during the loading phase include selecting the appropriate loading method, such as batch or real-time loading. Ensuring data quality and integrity during the loading process. Handling errors and exceptions, such as data validation failures or constraint violations. Optimizing loading performance for efficient data ingestion and processing. ETL tools and technologies. Several ETL tools and technologies are available to streamline and automate the ETL process, including traditional ETL tools. These include commercial tools like Informatica PowerCenter, IBM DataStage, and Microsoft SQL Server Integration Services, or SSIS. Open source ETL tools. Open source tools like Apache NiFi, Apache Airflow, and Talend Open Studio offer flexibility and cost-effectiveness. Cloud ETL services. Cloud-based ETL services such as AWS Glue, Google Cloud Dataflow, and Azure Data Factory provide scalability, agility, and managed infrastructure. Best practices for ETL processes. Data profiling. Understand the characteristics and quality of the data to guide transformation decisions. Incremental loading. Implement incremental loading to minimize processing time and resource consumption. Monitoring and logging. Monitor ETL jobs, track data lineage, and log errors for troubleshooting and auditing purposes. Scalability and resilience. Design ETL processes to scale horizontally and handle failures gracefully. Metadata management. Maintain metadata to document data lineage, transformations, and dependencies for better governance and transparency. By following best practices and leveraging ETL tools and technologies, organizations can streamline data integration, ensure data quality, and enable actionable insights from their data assets. 4.2 ELT. Extract, Load, Transform Paradigms. The ELT, Extract, Load, Transform Paradigm, offers an alternative approach to data integration and processing. In this paradigm, data is initially extracted from various sources without significant transformation. It is then loaded into a target storage system, such as a data lake or warehouse, before undergoing transformation as needed. During the extraction phase, data is retrieved from source systems, including databases, applications, APIs, or files. Extraction methods are chosen, ensuring data integrity and consistency. Following extraction, the data is loaded into the target storage system, such as a data lake or warehouse. This phase focuses on moving the raw data without extensive transformation while ensuring data quality and integrity. Once the data is loaded, the transformation stage occurs, where the data is cleaned, validated, and structured for analysis and consumption. Transformations include cleaning, normalization, aggregation, and enriching the data to prepare it for analysis. The ELT paradigm offers several advantages, including scalability, flexibility, and cost-effectiveness. It leverages the storage and processing capabilities of modern data storage systems, such as cloud-based data lakes and warehouses, without the need for additional ETL infrastructure. Considerations for ELT include data volume and complexity, data governance and security, and the tooling and infrastructure required for data storage, processing, and analysis. By adopting the ELT paradigm, organizations can streamline data integration, enable flexible data processing, and derive actionable insights from their data assets. 4.3. Stream processing and batch processing. Stream processing and batch processing are two fundamental approaches to handling data, each with its own characteristics, advantages, and use cases. Stream processing. Stream processing involves handling data in real time as it is generated or received. Here are some key features of stream processing. Low latency. Data is processed with minimal delay, enabling immediate analysis and action. Continuous processing. Stream processing systems continually ingest, process, and analyze data streams as they arrive. Event-driven. Stream processing is event-driven, reacting to each individual event or data point as it occurs. Scalability. Stream processing systems are designed to scale horizontally to handle high-volume data streams. Use cases. Stream processing is ideal for applications requiring real-time analytics, monitoring, alerting, and event-driven decision-making. Examples include fraud detection, real-time recommendations, IoT data processing, and monitoring systems. Batch processing. Batch processing involves collecting and processing data in large chunks or batches at scheduled intervals. Here are some key features of batch processing. High throughput. Batch processing systems handle data in large volumes, optimizing throughput and resource utilization. Scheduled processing. Data is processed periodically or at predefined intervals, rather than in real time. Data aggregation. Batch processing systems aggregate data over time periods, enabling historical analysis and reporting. Robustness. Batch processing is robust and fault-tolerant, handling failures and retries gracefully. Use cases. Batch processing is suitable for scenarios where real-time processing is not required, such as ETL, extract, transform, load operations, data warehousing, batch analytics, and reporting. Relationship and integration. While stream processing and batch processing serve different purposes, they can be complementary and integrated within an organization's data architecture. Hybrid processing. Organizations may use a combination of stream processing and batch processing techniques to meet diverse data processing needs. For example, stream processing may be used for real-time monitoring and alerting, while batch processing may be used for historical analysis and reporting. Lambda architecture. Lambda architecture combines batch processing and stream processing to handle both real-time and historical data processing. It involves parallel processing of data streams and batch data, integrating the results to provide a unified view. In summary, stream processing and batch processing offer different approaches to handling data, each suited for specific use cases and requirements. By understanding their characteristics and capabilities, organizations can design efficient and effective data processing pipelines to support their business needs. 4.4. Data cleaning and normalization. Data cleaning and normalization are essential steps in preparing data for analysis and modeling. Here's an overview of each process. Data cleaning. Data cleaning involves identifying and correcting errors, inconsistencies, and missing values in the dataset. Key tasks in data cleaning include handling missing values. Identify and address missing values in the dataset by imputing or removing them based on the context and impact on analysis. Removing duplicates. Identify and remove duplicate records or observations from the dataset to ensure data integrity and accuracy. Standardizing values. Standardize values across the dataset to ensure consistency, such as converting categorical values to a common format or unit. Correcting errors. Identify and correct errors in the data, such as typos, misspellings, or incorrect entries. Dealing with outliers. Identify and handle outliers in the data, either by removing them or applying transformations to mitigate their impact on analysis. Data normalization. Data normalization involves transforming and scaling data to a common scale or range. This process ensures that different variables are comparable and have equal influence on analysis and modeling. Key techniques in data normalization include min-max scaling. Rescale data to a specific range, such as 0 or 1, by subtracting the minimum value and dividing by the range. Z-score or Z-score standardization. Standardize data to have a mean of 0 and a standard deviation of 1, making it comparable across different variables. Robust scaling. Scale data using robust statistics, such as the median and interquartile range, to reduce the impact of outliers. Log transformation. Apply logarithmic transformation to data to reduce skewness and heteroscedasticity making it more suitable for certain types of analysis. Normalization techniques. Use normalization techniques specific to the data distribution and requirements, such as power transformations or Box-Cox transformations. Importance. Data cleaning and normalization are crucial for ensuring the quality, consistency, and reliability of data for analysis and modeling. They help improve the accuracy and effectiveness of machine learning algorithms, reduce bias and noise in the data, and facilitate meaningful insights and decision-making. By performing data cleaning and normalization as part of the data preparation process, organizations can ensure that their analyses and models are based on high-quality, standardized data, leading to more reliable and actionable results. Chapter 5. Data Pipeline Design and Orchestration. Data pipeline design and orchestration involve creating workflows to automate the movement and processing of data through various stages of a data pipeline. 5.1 Fundamentals of Data Pipeline Design. Designing a data pipeline involves structuring a workflow that automates the movement and processing of data from source to destination. Here are the key fundamentals. Define data sources. Identify the sources of data, including databases, files, APIs, or streaming platforms from which data will be extracted. Data extraction. Extract data from the identified sources using appropriate methods, such as querying databases, reading files, or consuming APIs. Data transformation. Transform the extracted data to meet the requirements of the target system or application. This may involve cleaning, filtering, aggregating, or enriching the data. Data loading. Load the transformed data into the target system or application, such as a data warehouse, data lake, or operational database. Error handling. Implement mechanisms to handle errors and exceptions during the data pipeline execution, such as retrying failed operations, logging errors, and alerting stakeholders. Monitoring and logging. Monitor the performance and health of the data pipeline in real time, logging key metrics and events to track its execution and identify bottlenecks or issues. Scalability and reliability. Design the data pipeline to scale horizontally to handle increasing data volumes and to be resilient to failures, ensuring continuous operation and data integrity. Security. Implement security measures to protect sensitive data throughout the pipeline, including encryption, access controls, and compliance with data protection regulations. Orchestration. Orchestrate the execution of the data pipeline, scheduling and coordinating individual tasks and workflows to ensure proper sequencing and dependencies. Automation. Automate the execution of the data pipeline to minimize manual intervention and ensure consistency, repeatability, and efficiency in data processing. By following these fundamentals, organizations can design robust and efficient data pipelines that enable seamless data integration, transformation, and analysis to support business objectives and decision-making. 5.2. Workflow Management Tools. Apache Airflow, Luigi, Prefect. Workflow management tools like Apache Airflow, Luigi, and Prefect are essential for orchestrating and automating data pipelines. Each tool offers unique features and capabilities. Apache Airflow allows users to create, schedule, and monitor workflows using directed acyclic graphs, or DAGs. It manages task dependencies, supports dynamic workflows, and scales horizontally to handle large-scale data processing. Airflow also provides built-in monitoring and alerting features. Luigi, developed by Spotify, defines workflows as task dependencies, allowing users to express complex data processing pipelines easily. It offers flexible configuration, central metadata repository, and integrates tightly with Python for task definition and execution. Luigi provides visibility into workflow execution through a web interface. Prefect is a modern workflow orchestration platform designed for building, running, and monitoring data workflows. It allows users to define workflows imperatively using Python code, supports dynamic DAG construction, and provides version control for workflows. Prefect also handles task failures and retries automatically, ensuring fault tolerance and reliable execution of workflows. Additionally, it integrates with monitoring and observability tools for performance tracking and alerting. These workflow management tools empower organizations to streamline data pipeline orchestration, automate repetitive tasks, and ensure efficient data processing and analysis. 5.3. Monitoring and maintaining data pipelines. Monitoring and maintaining data pipelines are crucial tasks to ensure the reliability, performance, and accuracy of data processing workflows. Here's how to effectively monitor and maintain data pipelines. Monitoring. Metrics collection. Monitor key metrics such as data throughput, latency, error rates, and resource utilization to assess pipeline performance and health. Alerting. Set up alerts for abnormal conditions, failures, or performance degradation to proactively identify and address issues. Logging. Log pipeline execution details, including task statuses, timestamps, and error messages for troubleshooting and auditing purposes. Dashboarding. Use visualization tools to create dashboards that provide real-time insights into pipeline status, performance trends, and operational metrics. End-to-end monitoring. Monitor the entire data pipeline, from data ingestion to processing and output, to ensure data integrity and completeness. Maintenance. Regular checks. Perform regular checks and audits of the data pipeline to identify potential issues, bottlenecks, or data quality issues. Dependency updates. Keep software dependencies, libraries, and frameworks up to date to leverage bug fixes, performance improvements, and new features. Performance optimization. Optimize pipeline performance by identifying and addressing bottlenecks, inefficiencies, or resource constraints. Scaling. Scale the data pipeline horizontally or vertically to handle increasing data volumes, user loads, or processing requirements. Backup and disaster recovery. Implement backup and disaster recovery mechanisms to ensure data availability and recoverability in case of failures or disasters. Automation. Scheduled maintenance. Automate routine maintenance tasks such as data backups, software updates, and systems checks to minimize manual intervention and ensure consistency. Self-healing mechanisms. Implement self-healing mechanisms to automatically recover from failures, retry failed tasks, and resume pipeline execution without human intervention. Continuous integration or continuous deployment. CI or CD. Use CI or CD practices to automate pipeline deployment, testing, and rollout of changes, ensuring rapid and reliable updates to the pipeline. Version control. Maintain version control for pipeline configurations, code, and dependencies to track changes, roll back to previous versions, and collaborate on pipeline development. Collaboration and documentation. Documentation. Document pipeline architecture, design decisions, dependencies, and operational procedures to facilitate troubleshooting, onboarding, and knowledge sharing. Collaboration. Foster collaboration and communication among team members responsible for designing, developing, and maintaining the data pipeline to ensure alignment and coordination. By effectively monitoring and maintaining data pipelines, organizations can ensure the reliability, performance, and scalability of their data processing workflows, enabling them to derive meaningful insights and make informed decisions based on high-quality data. 5.4. Error handling and data recovery strategies. Error handling and data recovery strategies are pivotal components in maintaining the resilience and reliability of data pipelines. In terms of error handling, it's imperative to first detect errors promptly. This involves setting up mechanisms to monitor task statuses, logs, and metrics for anomalies. Once an error is detected, detailed error messages should be logged, including timestamps and contextual information, to aid in troubleshooting. Additionally, alerts and notifications should be configured to promptly inform stakeholders of critical errors, allowing for timely intervention. Retry mechanisms are also crucial. Failed tasks or operations should be automatically retried with configurable retry intervals and back-off strategies to handle transient errors effectively. Furthermore, designing pipelines with fault tolerance in mind, using redundancy, checkpointing, and task isolation helps minimize the impact of failures on pipeline execution. Regarding data recovery, implementing regular backups of critical data and metadata is essential. Incremental processing can be employed to process only the changes or deltas, facilitating faster recovery and reducing data loss in case of failures. Transaction management with rollback mechanisms ensures data consistency and integrity, allowing for the reverting of changes in case of errors. Checkpointing mechanisms enable the periodic saving of the pipeline state, allowing for resumption from the last successful checkpoint in case of interruptions. Data replication across multiple storage locations or data centers ensures redundancy and resilience against data loss or corruption. Data validation techniques such as checksums and anomaly detection help detect and correct errors early in the pipeline. For disaster recovery planning, it's vital to develop a comprehensive plan outlining procedures, roles, and responsibilities for responding to major incidents or disasters. This includes maintaining backup sites or redundant infrastructure in geographically diverse locations, implementing failover mechanisms to switch to backup systems automatically, and conducting regular drills and testing to validate recovery procedures and train personnel on response protocols. By implementing robust error handling and data recovery strategies, organizations can minimize downtime, mitigate data loss, and maintain the reliability and availability of their data pipelines, ensuring continuity of operations and preserving data integrity. Chapter 6: Big Data Technologies. Big data technologies encompass a wide range of tools and frameworks designed to handle large volumes of structured, semi-structured, and unstructured data. 6.1 Hadoop Ecosystem. The Hadoop ecosystem comprises a suite of open-source software tools and frameworks designed to process, store, and analyze large volumes of data across distributed computing clusters. Here are some key components of the Hadoop ecosystem. Core components. 1. Hadoop Distributed File System, or HDFS. A distributed file system that provides scalable and reliable storage for large datasets across clusters of commodity hardware. 2. MapReduce. A programming model and processing engine for parallel computation of large datasets across distributed clusters. It divides data processing tasks into smaller subtasks, which are executed in parallel across nodes in the cluster. Data processing frameworks. Apache Spark. A fast and general-purpose distributed computing engine that supports in-memory processing and offers high-level APIs for batch processing, interactive queries, streaming data, and machine learning. Apache Hive. A data warehouse infrastructure built on top of Hadoop for querying and analyzing large datasets stored in HDFS using an SQL-like query language called HiveQL. Apache Pig. A platform for analyzing large datasets using a high-level scripting language called Pig Latin. It abstracts the complexities of MapReduce programming and enables data transformations and analysis. Data ingestion and integration. Apache Flume, a distributed, reliable, and available service for efficiently collecting, aggregating, and moving large amounts of streaming data into Hadoop. Apache Sqoop, a tool designed for efficiently transferring bulk data between Apache Hadoop and structured data stores such as relational databases. Apache Kafka, a distributed event streaming platform that enables the ingestion and processing of high volumes of real-time data streams. Resource management and orchestration. Apache Yarn, or YARN, or yet another resource negotiator. A resource management and job scheduling framework for managing computing resources in Hadoop clusters. It allows multiple data processing engines to run on the same cluster. Apache Oozie, a workflow scheduler system for managing Hadoop jobs. It allows users to define, schedule, and run complex workflows of Hadoop jobs. Storage formats and query engines. Apache Parquet, a columnar storage format optimized for storing and querying large datasets efficiently in Hadoop. Apache ORC, or Optimized Row Columnar, another columnar storage format that provides fast read access and efficient compression for Hive data warehouse queries. Data visualization and business intelligence. Apache Zeppelin, a web-based notebook for interactive data analysis with support for multiple programming languages, including Scala, Python, SQL, and others. Apache Superset, a modern, enterprise-ready business intelligence web application for exploring and visualizing data stored in Hadoop and other data sources. The Hadoop ecosystem continues to evolve with new projects and technologies emerging to address the challenges of processing and analyzing big data. 6.2 Apache Spark, Architecture and Use Cases. Apache Spark is an open-source distributed computing system that provides an efficient and flexible framework for processing large-scale data. Its architecture and versatility make it suitable for a wide range of use cases. Let's explore its architecture and some common use cases. Apache Spark Architecture. Apache Spark's architecture is based on a distributed computing model and consists of the following key components. Driver program, the main program that coordinates the execution of Spark jobs. It splits the application into tasks, schedules them for execution, and manages the overall execution flow. Cluster Manager manages the allocation of resources, e.g. memory, CPU cores, across the cluster and coordinates the execution of Spark applications. Popular cluster managers include Apache Yarn, Apache Mesos, and Kubernetes. Executors, worker processes that execute tasks assigned by the driver program. Executors are launched on worker nodes in the cluster and manage the execution of individual tasks, caching data in memory or disk storage for efficient processing. RDDs, or Resilient Distributed Datasets. Spark's primary abstraction for representing and manipulating data distributed across the cluster. RDDs are immutable, fault-tolerant collections of records that can be transformed and processed in parallel across multiple nodes. DAG, or Directed Acyclic Graph Scheduler, converts Spark jobs into a directed acyclic graph of stages and tasks, optimizing task execution and resource utilization. Transformations and actions. Spark provides a rich set of transformations, e.g. map, filter, reduce, and actions, e.g. collect, count, or save, for processing and analyzing data in parallel. Use cases. 1. Batch processing. Apache Spark is widely used for batch processing tasks such as ETL, extract, transform, load, data cleaning, transformation, and aggregation. It can efficiently process large volumes of data stored in distributed file systems or databases. 2. Stream processing. Spark streaming, a component of Apache Spark, enables real-time processing and analysis of streaming data. It can ingest data from various sources, e.g. Kafka, Flume, Kinesis, and perform continuous computations on the data stream. 3. Machine learning. Spark ML-lib provides a scalable machine learning library for training and deploying machine learning models on large datasets. It supports a wide range of algorithms for classification, regression, clustering, and collaborative filtering. 4. Graph processing. Spark GraphX offers a distributed graph processing framework for analyzing large-scale graph datasets. It provides APIs for graph construction, manipulation, and computation of graph algorithms. 5. Interactive data analysis. Apache Spark can be used for interactive data analysis and exploration through tools like Spark SQL and data frames. Users can execute SQL queries or perform data manipulations interactively on distributed datasets. 6. Real-time analytics. Spark's ability to process streaming data in near real-time makes it suitable for applications requiring real-time analytics, such as fraud detection, monitoring, and personalized recommendations. Overall, Apache Spark's architecture and rich set of features make it a versatile framework for processing and analyzing large-scale data across a variety of use cases, from batch and stream processing to machine learning and graph analytics. 6.3. Distributed computing and storage solutions. Distributed computing and storage solutions are integral components of modern data processing architectures, enabling organizations to efficiently handle large volumes of data across distributed clusters of servers. In distributed computing, tasks and computations are distributed across multiple nodes or machines in a cluster, allowing for parallel execution and improved performance. This approach enables organizations to process vast amounts of data in a scalable and fault-tolerant manner. Distributed storage solutions, on the other hand, provide scalable and reliable storage for large datasets across distributed clusters. These solutions typically replicate data across multiple nodes to ensure redundancy and fault tolerance, minimizing the risk of data loss and downtime. Popular distributed computing frameworks include Apache Hadoop and Apache Spark, which provide tools and libraries for processing and analyzing large-scale data across distributed clusters. These frameworks leverage distributed storage solutions such as Hadoop Distributed File System, or HDFS, and cloud storage services to store and access data efficiently. Other distributed storage solutions include distributed databases, e.g. Apache Cassandra or MongoDB, object storage systems, e.g. Amazon S3 or Google Cloud Storage, and distributed file systems, e.g. GlusterFS or Ceph. These solutions offer scalability, reliability, and high availability, making them suitable for storing and managing large volumes of data in distributed environments. 6.4. Performance tuning and optimization. Performance tuning and optimization are essential processes to ensure the efficient operation of data systems and applications. Here are some key strategies and best practices for optimizing performance. Profiling and monitoring. Identify performance bottlenecks by profiling and monitoring system metrics, resource utilization, and query execution times. Use tools like monitoring dashboards, profiling tools, and logging to gather insights into system behavior. Query optimization. Optimize database queries by analyzing query execution plans, indexing strategies, and data access patterns. Use techniques such as query rewriting, indexing, partitioning, and denormalization to improve query performance. Data partitioning. Partition large datasets into smaller chunks based on key criteria, e.g. date, location, to distribute data evenly and improve parallelism in data processing and retrieval. Parallel processing. Leverage parallel processing techniques to distribute computational tasks across multiple processing units or nodes, maximizing throughput and reducing latency. Use frameworks like Apache Spark for distributed data processing and analysis. Resource allocation. Allocate resources, e.g. CPU, memory, or storage, optimally based on workload characteristics, resource demands, and performance requirements. Use dynamic resource allocation mechanisms to scale resources up or down based on demand. Caching. Implement caching mechanisms to store frequently accessed data or computation results in memory or a fast access storage layer. This reduces the need for repeated computation and improves response times for subsequent requests. Compression. use data compression techniques to reduce storage space and bandwidth requirements, especially for large datasets and network transfers. Choose compression algorithms based on data characteristics and performance trade-offs. Data serialization. Optimize data serialization and deserialization processes by choosing efficient serialization formats, e.g. Avro or Protobuf, and libraries. Minimize overhead and processing time by selecting lightweight serialization methods. Code optimization. Optimize application code and algorithms for performance by identifying and eliminating inefficiencies, reducing redundant operations, and improving algorithmic complexity. Use profiling tools and performance benchmarks to identify hotspots and areas for optimization. Hardware and infrastructure optimization. Optimize hardware configurations, infrastructure components, and network topology to maximize performance and minimize latency. Consider factors such as CPU architecture, memory speed, network bandwidth, and storage throughput. Benchmarking and testing. Benchmark system performance under various workloads, scenarios, and configurations to identify performance limits, bottlenecks, and areas for improvement. Use load testing, stress testing, and performance benchmarks to validate system performance and scalability. By applying these performance tuning and optimization strategies systematically, organizations can achieve optimal performance, scalability, and reliability in their data systems and applications, ensuring efficient data processing and analysis across diverse workloads and environments. Chapter 7: Cloud-Based Data Engineering. Cloud-based data engineering involves designing and implementing data pipelines, processing systems, and analytics solutions using cloud services and platforms. 7.1 Cloud Platforms Overview: AWS, Azure, Google Cloud. Cloud platforms, including Amazon Web Services or AWS, Microsoft Azure, and Google Cloud Platform or GCP, offer a wide range of cloud services and solutions for building, deploying, and managing applications and data in the cloud. Here's an overview of each platform. 1. Amazon Web Services, or AWS. Compute Services. AWS offers Elastic Compute Cloud, or EC2, for scalable virtual servers, Lambda for serverless computing, and Elastic Container Service, or ECS, for container orchestration. Storage Services. AWS provides Simple Storage Service, or S3, for scalable object storage, Elastic Block Store, or EBS, for block storage, and Glacier for archival storage. Database Services. AWS offers managed database services such as Amazon RDS, or Relational Database Service, Amazon DynamoDB for NoSQL databases, and Amazon Redshift for data warehousing. Analytics and Big Data. AWS provides services like Amazon EMR or Elastic MapReduce for big data processing, Amazon Athena for querying data stored in S3, and Amazon Kinesis for real-time data streaming. Machine learning. AWS offers services like Amazon SageMaker for building, training, and deploying machine learning models, and Amazon Comprehend for natural language processing. 2. Microsoft Azure. Compute services. Azure provides virtual machines, or VMs, with Azure Virtual Machines, serverless computing with Azure Functions, and container orchestration with Azure Kubernetes Service, or AKS. Storage services. Azure offers blob storage for scalable object storage, Azure Disk Storage for block storage, and Azure Data Lake Storage for big data analytics. Database services. Azure provides Azure SQL Database for relational databases, Azure Cosmos DB for NoSQL databases, and Azure Synapse Analytics for data warehousing. Analytics and big data. Azure offers services like Azure HD Insight for big data processing, Azure Data Lake Analytics for analytics at scale, and Azure Stream Analytics for real-time data processing. Machine learning. Azure provides services like Azure Machine Learning for building, training, and deploying machine learning models, and Azure Cognitive Services for AI-powered APIs. 3. Google Cloud Platform, or GCP. Compute services. GCP offers compute engine for virtual machines, cloud functions for serverless computing, and Google Kubernetes engine, or GKE, for container orchestration. Storage services. GCP provides cloud storage for scalable object storage, persistent disk for block storage, and BigQuery for data warehousing and analytics. Database services. GCP offers Cloud SQL for managed relational databases, Cloud Firestore for NoSQL databases, and Bigtable for scalable and high-performance NoSQL databases. Analytics and big data. GCP provides services like Dataproc for big data processing, Dataflow for real-time and batch data processing, and BigQuery for analytics at scale. Machine learning. GCP offers services like AI Platform for building and deploying machine learning models, and Cloud Auto ML for custom machine learning models. Each cloud platform provides a comprehensive set of services and solutions for various use cases, allowing organizations to leverage cloud computing resources to build scalable, resilient, and cost-effective applications and data solutions. 7.2. Data storage and processing in the cloud. Data storage and processing in the cloud involve utilizing cloud services and platforms to efficiently manage, store, and analyze data. Here's how it typically unfolds. Cloud providers offer a variety of storage options tailored to different data types, access patterns, and performance needs. Object storage, suitable for unstructured data like files and multimedia, is exemplified by Amazon S3, Google Cloud Storage, and Azure Blob Storage. Block storage, providing raw storage volumes attachable to virtual machines, is exemplified by Amazon EBS, Google Persistent Disks, and Azure Disk Storage. File storage, facilitating shared file storage for applications and users, is seen in Amazon EFS, Google Cloud File Store, and Azure Files. For databases, managed services like Amazon RDS, Google Cloud SQL, Azure SQL Database, Amazon DynamoDB, Google Cloud Firestore, and Azure Cosmos DB offer relational and NoSQL database solutions. Cloud platforms furnish an array of tools and services for processing and analyzing data at scale. Batch processing, executed on managed Hadoop and Spark clusters through services like Amazon EMR, Google Dataproc, and Azure HD Insight, handles large data volumes in batch mode. Stream processing services like Amazon Kinesis, Google Cloud Dataflow, and Azure Stream Analytics enable real-time processing of streaming data for instantaneous analytics. Serverless computing platforms such as AWS Lambda, Google Cloud Functions, and Azure Functions facilitate serverless execution of code, ideal for event-driven data processing tasks. Data warehousing solutions like Amazon Redshift, Google BigQuery, and Azure Synapse Analytics offer managed data warehouse capabilities for complex analytics queries on extensive datasets. Integration and orchestration tools streamline data workflows across different services. Services like AWS Glue, Google Cloud Data Transfer, and Azure Data Factory support data movement between various storage systems and processing services. Workflow orchestration tools such as Apache Airflow, AWS Step Functions, and Google Cloud Composer enable the orchestration of complex data workflows, task scheduling, and monitoring. Data catalogs such as AWS Glue Data Catalog, Google Cloud Data Catalog, and Azure Data Catalog centralize metadata management and discovery for data assets across the cloud environment. By harnessing cloud storage and processing services, organizations gain scalability, flexibility, and cost-effectiveness in managing and analyzing their data, empowering them to derive valuable insights and drive business outcomes efficiently. 7.3. Cloud Data Warehousing. Snowflake, Redshift, BigQuery. Cloud data warehousing solutions, including Snowflake, Amazon Redshift, and Google BigQuery, provide managed data warehousing services for storing and analyzing large data sets in the cloud. Here's an overview of each platform. Snowflake. Snowflake is a cloud-native data warehousing platform known for its unique architecture that separates compute, storage, and query processing. Key features include multi-cluster shared data architecture. Snowflake's architecture separates storage and compute, allowing multiple compute clusters to access the same data concurrently. Automatic scaling. Snowflake automatically scales compute resources up or down based on workload demand, enabling users to handle varying workloads without manual intervention. Fully managed service. Snowflake is a fully managed service, handling tasks such as infrastructure provisioning, maintenance, and performance tuning, reducing the operational overhead for users. Native support for semi-structured data. Snowflake natively supports semi-structured data formats like JSON, Avro, and Parquet, enabling users to ingest and query diverse data types seamlessly. Amazon Redshift. Amazon Redshift is a fully managed data warehousing service that offers fast query performance and scalability. Key features include massively parallel processing architecture, or MPP architecture. Redshift distributes data and queries across multiple nodes for parallel processing, enabling fast query performance on large datasets. Columnar storage. Redshift stores data in a columnar format, optimizing storage and query performance by minimizing IRO and maximizing compression. Integration with AWS ecosystem. Redshift seamlessly integrates with other AWS services such as S3 for data storage, AWS Glue for data cataloging, and AWS Lambda for event-driven processing. Advanced analytics. Redshift supports advanced analytics capabilities, including machine learning integration, geospatial analysis, and time series analysis. Google BigQuery. Google BigQuery is a serverless, fully managed data warehouse that offers high-performance analytics with built-in machine learning capabilities. Key features include serverless architecture. BigQuery automatically scales compute and storage resources based on query demand, eliminating the need for manual provisioning or capacity planning. Columnar storage and execution. BigQuery stores data in a columnar format and executes queries using a distributed, parallelized processing engine, resulting in fast query performance on large datasets. Integration with Google Cloud Platform. BigQuery integrates seamlessly with other Google Cloud Platform services, such as Google Cloud Storage for data storage, Google Data Studio for visualization, and Google Cloud AI for machine learning. Machine learning integration. BigQuery offers built-in machine learning capabilities for predictive analytics, anomaly detection, and natural language processing, enabling users to derive insights directly from their data. Each of these cloud data warehousing platforms offers unique features and capabilities, enabling organizations to build scalable, high-performance data warehouses and derive valuable insights from their data effectively. 7.4. Cost management and best practices. Cost management is crucial when utilizing cloud services to ensure efficiency, optimize spending, and maximize return on investment. Here are some best practices for managing costs in the cloud. Monitor usage and spending. Regularly monitor cloud usage and spending using monitoring tools and dashboards provided by cloud providers. Identify areas of high usage and spending to understand where costs are being incurred. Implement cost allocation tags. Use cost allocation tags to allocate costs to specific projects, departments, or teams. This allows for better cost tracking and accountability, enabling you to identify cost drivers and optimize spending. Right-size resources. Optimize resource utilization by right-sizing instances, storage, and other resources based on actual usage and performance requirements. Choose instance types and sizes that best fit your workload needs to avoid over-provisioning and unnecessary costs. Utilize reserved instances and savings plans. Take advantage of reserved instances, savings plans, or similar commitments offered by cloud providers to secure discounted pricing for long-term usage. Committing to reserved capacity can result in significant cost savings over pay-as-you-go pricing. Use spot instances and preemptible VMs. Leverage spot instances, or AWS, or preemptible VMs, or GCP, for non-critical workloads and tasks that can tolerate interruptions. These instances offer significant cost savings compared to regular on-demand instances, but may be reclaimed by the cloud provider with short notice. Set budgets and alerts. Define budgets and setup alerts to notify you when spending exceeds predefined thresholds. This helps prevent unexpected cost overruns and allows for timely intervention to adjust resource usage or optimize spending. Implement auto-scaling and auto-shutdown. Use auto-scaling policies to automatically adjust resources based on workload demand, scaling up during peak periods, and scaling down during periods of low activity. Additionally, configure auto-shutdown policies for non-production resources to minimize costs when not in use. Optimize data transfer costs. Minimize data transfer costs by optimizing data transfer patterns, leveraging caching and content delivery networks, or CDNs, and choosing the right data transfer options based on data access patterns and geographical locations. Leverage cloud-native services. Take advantage of cloud-native services and managed services provided by cloud providers, as they often offer a more cost-effective and efficient alternative to self-managed infrastructure. Examples include serverless computing, managed databases, and analytics services. Regularly review and optimize. Continuously review your cloud environment, identify opportunities for optimization, and implement cost-saving measures accordingly. Cloud cost optimization is an ongoing process that requires regular monitoring, analysis, and adjustment. By following these best practices and adopting a proactive approach to cost management, organizations can optimize their cloud spending, reduce unnecessary costs, and maximize the value derived from cloud services. Chapter 8: Data Security and Governance. Data security and governance are critical aspects of managing data effectively, ensuring confidentiality, integrity, and availability while complying with regulatory requirements. 8.1 Data Privacy Laws and Regulations. Data privacy laws and regulations govern the collection, use, and protection of personal data to ensure individuals' privacy rights are respected. Here are some key data privacy laws and regulations. General Data Protection Regulation, or GDPR. Enforced by the European Union, or EU, GDPR aims to protect the personal data of EU citizens. It imposes strict requirements on how organizations collect, process, and store personal data, including obtaining consent, providing data subjects with access to their data, and implementing appropriate security measures. California Consumer Privacy Act, or CCPA. Enacted in California, CCPA grants California residents certain rights over their personal information held by businesses, such as the right to know what data is collected, the right to opt out of data sales, and the right to request deletion of their data. Health Insurance Portability and Accountability Act, or HIPAA. HIPAA regulates the use and disclosure of protected health information, or PHI, by healthcare providers, health plans, and other covered entities. It requires safeguards to protect the confidentiality, integrity, and availability of PHI. Payment Card Industry Data Security Standard, or PCI DSS. PCI DSS sets security standards for organizations that handle payment card data to prevent credit card fraud and data breaches. It mandates the use of security controls such as encryption, access controls, and regular security assessments. Personal Information Protection and Electronic Documents Act, or PIPEDA. PIPEDA is Canada's federal privacy law that governs the collection, use, and disclosure of personal information by private sector organizations. It requires obtaining consent for data collection, limiting data use, and safeguarding personal information. Children's Online Privacy Protection Act, or COPPA, or COPPA. COPPA regulates the online collection of personal information from children under the age of 13 in the United States. It requires obtaining parental consent, providing notice of data practices, and implementing safeguards to protect children's privacy. Brazilian General Data Protection Law, or LGPD. Similar to GDPR, LGPD is Brazil's data protection law that regulates the processing of personal data of individuals in Brazil. It establishes principles for data processing, data subject rights, and data breach notification requirements. Personal Data Protection Bill, or PDPB. The proposed data protection law in India aims to regulate the processing of personal data and establish rights and obligations for data fiduciaries and data subjects. It includes provisions for data localization, data transfer, and data protection authority. These are just a few examples of data privacy laws and regulations that organizations worldwide must comply with to protect individuals' privacy rights and avoid legal and financial consequences resulting from data breaches or non-compliance. 8.2. Implementing data security measures. Implementing data security measures is crucial to protect sensitive information from unauthorized access, breaches, and misuse. Here are key steps to implement effective data security measures. 1. Data classification. Identity-sensitive data. Determine the types of data your organization collects, processes, and stores, including personal, financial, and confidential information. Classified data. Categorize data based on its sensitivity and importance, such as public, internal, confidential, and regulated data, to prioritize security measures accordingly. 2. Access control. Role-based access control, or RBAC. Implement RBAC to restrict access to sensitive data based on users' roles and responsibilities, ensuring that only authorized users can access and modify data. Least privilege principle. Grant users the minimum level of access required to perform their job functions, limiting the risk of unauthorized access and data breaches. Multi-factor authentication, or MFA. Enforce MFA for accessing sensitive systems and data, requiring users to provide additional verification beyond passwords such as OTP codes or biometric scans. 3. Encryption. Data encryption. Encrypt data at rest and in transit using strong encryption algorithms to protect data from unauthorized access, ensuring that even if data is compromised, it remains unreadable without decryption keys. Key management. Implement robust key management practices to securely generate, store, and rotate encryption keys, ensuring that encryption keys are protected and accessible only to authorized users. 4. Data masking and anonymization. Data masking. Mask sensitive data such as personally identifiable information, or PII, or financial information in non-production environments to prevent unauthorized exposure during testing and development. Anonymization. Anonymize or pseudonymize sensitive data where feasible to remove or obscure identifying information, reducing the risk of data breaches and protecting individuals' privacy. 5. Monitoring and logging. Activity monitoring. Implement real-time monitoring of user activities, data access, and system events to detect suspicious behavior, unauthorized access attempts, and potential security threats. Audit logging. Enable comprehensive audit logging of user actions, data accesses, and system changes to track and review security-related events for compliance, investigation, and forensic analysis. 6. Data loss prevention, or DLP. DLP solutions. Deploy DLP solutions to identify, monitor, and prevent the unauthorized transmission or exfiltration of sensitive data through email, web applications, and other communication channels. Data discovery. Use DLP tools to scan and identify sensitive data across your organization's systems, applications, and storage repositories, ensuring that sensitive data is properly protected. 7. Security training and awareness. Employee training. Provide regular security training and awareness programs to educate employees about data security best practices, policies, and procedures, empowering them to recognize and respond to security threats effectively. Incident response. Establish incident response procedures and train employees on how to report security incidents, respond to breaches, and mitigate the impact of security incidents on data security and business operations. By implementing these data security measures systematically and proactively, organizations can strengthen their defenses against security threats, protect sensitive information, and maintain compliance with regulatory requirements. 8.3. Data governance frameworks. Data governance frameworks provide structured approaches to managing and protecting data assets throughout their life cycle, ensuring data quality, integrity, and compliance. Here are some key data governance frameworks. 1. DAMA-DMBOK, or DAMA-DMBOK, Data Management Body of Knowledge. Overview. Developed by the Data Management Association, or DAMA, DAMA-DMBOK provides a comprehensive framework for data management practices, principles, and disciplines. Components. It covers various aspects of data management, including data governance, data architecture, data modeling, data quality, data security, and metadata management. Key principles. DAMA-DMBOK emphasizes the importance of data governance as a foundational component of effective data management, highlighting principles such as accountability, transparency, integrity, and compliance. 2. COBIT, C-O-B-I-T, Control Objectives for Information and Related Technologies. Overview. COBIT is a framework developed by ISACA, ISACA, Information Systems Audit and Control Association, for governance and management of enterprise IT. Components. COBIT provides a set of controls, processes, and best practices for IT governance, including data governance. It focuses on aligning IT with business objectives, managing risks, and ensuring compliance. Key principles. COBIT emphasizes the need for clear policies, procedures, and controls to govern data assets effectively, with a focus on accountability, transparency, and risk management. 3. TOGAF or TOGAF, the Open Group Architecture Framework. Overview. TOGAF is a widely used framework for enterprise architecture development, maintenance, and governance. Components. TOGAF provides a structured approach to designing, planning, implementing, and governing enterprise architectures, including data architectures. Key principles. TOGAF emphasizes the importance of data governance in supporting business objectives, ensuring data consistency, integrity, and interoperability across the enterprise architecture. 4. ISO/IEC 38500, Corporate Governance of Information Technology. Overview. ISO/IEC 38500 is an international standard that provides guidance on the governance of IT within organizations. Components. It outlines principles, practices, and responsibilities for governing IT to ensure alignment with business goals, manage risks, and optimize IT investments. Key principles. ISO/IEC 38500 emphasizes the role of the board and senior management in governing IT, including data governance, to ensure that IT decisions support business objectives and comply with legal and regulatory requirements. 5. NIST Cybersecurity Framework. Overview. Developed by the National Institute of Standards and Technology, NIST, the cybersecurity framework provides guidance for managing cybersecurity risks. Components. While primarily focused on cybersecurity, the framework includes components related to data governance, such as identifying, protecting, detecting, responding to, and recovering from cybersecurity events. Key principles. The NIST Cybersecurity Framework emphasizes the importance of data governance in protecting sensitive data from cybersecurity threats, ensuring data confidentiality, integrity, and availability. By adopting and implementing these data governance frameworks, organizations can establish structured approaches to managing and protecting their data assets effectively, ensuring data quality, integrity, and compliance with regulatory requirements. 8.4. Auditing and compliance. Auditing and compliance are essential components of data governance, ensuring that organizations adhere to regulations, standards, and internal policies related to data management and security. Here are key aspects of auditing and compliance. Regulatory compliance. Identify applicable regulations. Determine the regulatory requirements that apply to your organization based on factors such as industry, geographic location, and the type of data collected and processed. Understand requirements. Thoroughly review relevant regulations such as GDPR, CCPA, HIPAA, PCI, DSS, and others to understand their requirements regarding data protection, privacy, security, and reporting. Implement controls. Implement controls and measures to ensure compliance with regulatory requirements, such as data encryption, access controls, audit trails, and data breach response procedures. Internal policies and standards. Develop data governance policies. Establish internal data governance policies and standards that align with regulatory requirements and best practices, defining roles, responsibilities, processes, and controls for managing data effectively. Enforce policies. Enforce compliance with internal policies through regular monitoring, audits, and enforcement mechanisms, ensuring that employees adhere to data governance practices and procedures. Update policies. Continuously review and update data governance policies and standards to reflect changes in regulations, technology, business practices, and organizational needs, ensuring ongoing compliance and effectiveness. Auditing processes. Conduct regular audits. Perform regular audits of data management practices, controls, and systems to assess compliance with regulatory requirements and internal policies, identifying gaps, vulnerabilities, and areas for improvement. External audits. Engage third-party auditors or compliance experts to conduct independent assessments of data governance practices and compliance with regulatory requirements, providing objective insights and recommendations. Internal audits. Establish internal audit processes and teams to conduct periodic reviews and assessments of data governance practices, controls, and compliance efforts, ensuring alignment with regulatory requirements and organizational goals. Documentation and reporting. Maintain documentation. Maintain detailed documentation of data governance practices, policies, controls, and audit findings to demonstrate compliance with regulatory requirements and facilitate accountability and transparency. Generate reports. Generate regular reports on data governance activities, audit findings, compliance status, and remediation efforts to senior management, stakeholders, regulatory authorities, and other relevant parties. Respond to findings. Take prompt action to address audit findings, non-compliance issues, and recommendations. Implementing corrective actions, controls, and measures to mitigate risks and improve data governance practices. By implementing robust auditing and compliance processes, organizations can ensure that they effectively manage data risks, protect sensitive information, and maintain trust with customers, partners, and regulatory authorities. You have been listening to Data Engineering, Analyzing Big Data and Modern Data. Written by Phil Gilbert. Narrated by Kevin Brooker.